the video how do hot air balloon is stays up and the strange physics that makes hurricane so powerful. These videos are by Be Smart YouTube channel, which explains the uh, fascinating physics behind two very different phenomena. So talking about how do hot air balloons stay up, these are the perfect example of Beyonce in action, using the basic principle of physics to lift up basket passengers and the balloon itself into the sky. So the key idea is density and the behavior of gases. So according to the ideal gas law, PV is equals to nRT. When you heat a gas, its molecules move faster and spread out. This increases the volume it occupies and decreases its density. Inside a hot air balloon, burner heats the air, making it less dense than the cooler air outside. Because warm air is lighter, it rises through the cooler, denser air. The balloon rises because of the buoyant force, the upward force exerted by the surrounding air, much like how a boat floats on water. So this concept is similar to Archimedes' principle. If an object displaces a fluid that weighs more than object itself, it will float. In this case, the hot air inside the balloon displaces cooler air outside. If the total weight of the balloon is less than the weight of the air it displaces, it will lift off the ground. So to descent, pilots allow their air inside to cool, increasing its density, which causes the balloon to sink. To go higher, they turn on the burners again, but there is no steering wheel. Pilots maneuver by ascending or descending into wind currents at different altitudes that are moving in various directions. So ultimately, hot air balloons float because of a simple balance between gravity pulling down and buoyant force pushing up. It's an elegant dance of thermodynamics, air pressure, and fluid dynamics, simple physics with breathtaking results. So let's go into the second video, the strange physics that makes hurricanes so powerful. So in contrast to the peaceful float of a balloon, hurricanes are among the most destructive natural forces on earth. Yet at their core, they are also driven by temperature differences, pressure, and fluid dynamics, just on a much larger, more violent scale. So a hurricane begins as a cluster of thunderstorms over warm ocean waters. These storms act as engines, converting heat energy from the ocean into mechanical energy. As ocean water evaporates, it rises into the atmosphere. When that water vapor condenses into clouds, it releases latent heat, an immense amount of energy that fuel the storm further. This release heat warms the surrounding air, making it rise even more, drawing in more warm, moist air from the surface and setting up a self-reinforcing cycle. This process turns the hurricane into a heat engine. The fuel is warm water and the exhaust is the cool air, and precipitation expelled from top of the storm. The more heat it can pull from the ocean, the stronger the storm becomes. Let's talk about the Coriolis effect. So because the earth is rotating, moving air is deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This effect causes the storm system to spin, giving hurricanes their distinctive rotation. As the air is drawn inward toward the center, it conserves angular momentum, a principle of physics that says if something is spinning and its radius decreases, it spins faster. This causes wind speeds to dramatically increase near the eye of the hurricane, the calm center, surrounded by the most intense winds in the eye wall. So this video also touches on the impact of climate change. As ocean warms, more energy is available to fuel these massive storms. This does not necessarily mean there will be more hurricanes, but it likely means that the ones that do form will be more intense, longer lasting, and capable of carrying more moisturizer, leading to more rainfall and flooding. So whether it's a lifting balloon gently into the clouds or driving a storm across the ocean, the strange and elegant physics of our atmosphere is always at work.